If you're working out these notes in advance of the video, then good for you. That's great. I'm not going to work out all the stuff that came right above this because we don't really need it. But it's a good exercise in exploring what happens to a function defined as such, defined as a definite integral, where the variable that is changing is the variable in the integral. So we call this an accumulation function because as our variable gets bigger and bigger and bigger, we're accumulating more area underneath our curve. But the question is, if x is our variable and t dt, that's going to be kind of a dummy variable that can be anything at all. But then a is a constant. Then what does changing a do to the graph h of x, or the function h of x? So we could do this really quickly by taking the integral of 2t with respect to t and taking the integral of 1 with respect to t, evaluating this at x equals, or t equals a and t equals x and t equals a. And we'll get x squared plus x minus a squared plus a. Okay, remember that h of x equals this thing right here, and x squared changes as x changes as x changes, but this a squared plus a is a constant because a is a constant. So what we're talking about here is all the variable stuff stays the same if we change a, but the constant is just going to make us have a vertical shift, right? A vertical shift. So if we have a vertical shift, then what does that do to the derivative? Well, it does absolutely nothing, right? Because h prime of x is going to equal, well, derivative of x squared is 2x, derivative of x is 1, and regardless of the value of a, we're subtracting a constant, and that's not going to affect our derivative. So what effect? None. So we see this pattern here where the integrand 2t plus 1 becomes 2x plus 1. And that's what happens when you take the derivative of an accumulation function. And that's the second fundamental theorem of calculus. It's basically saying that when you take the derivative of the integral, they cancel each other out. There is that extra little piece where we replace the dummy variable with the variable in our bounds. So this is going to be not f of t, but f of x. But that's really it. It's a really quick process. Don't spend the time doing this extra step of taking the antiderivative and evaluating it at two different places and subtracting the two values, and then taking the derivative. Just go ahead and realize, oh, the derivative and the integral are going to cancel each other out. Okay? I'm not even going to worry about this. Let's just completely ignore that. So in a problem that looks completely impossible like this, I mean, I don't know how to take the antiderivative of the cube root of t squared minus tangent of 5t minus 6. Do you? Well, anyway, we don't have to, because we're taking the derivative of the integral from 5 to x of that mess, dt. So all we have to do is realize, oh, the derivative and the integral cancel each other out, and the variable gets replaced with the x. So that's going to be the cube root of x squared minus tangent of 5x minus 6. Arg. So what do we do with this 5? Absolutely nothing. We don't do anything with that 5 because it's a constant. All right, cool. So that's it. We're done with that problem. So next up, we have, oh, well, we're just going to do the same thing here, right? Well, they're throwing us a curveball at this point because notice how the x is in the bottom now. So let's not forget the properties of integrals. We can switch this around to make a 90 on the bottom and an x on the top, provided we make sure we flip it from a positive to a negative, right? So we're changing the direction of our variables, our interval of integration. So that means that we are going to flip the sign of our answer. S-I-G-N sign, not to be confused with the sign function here. Okay, so let's remember also that this is not the same thing as sine squared of t. This is sine of t times t, which is a very different thing and something that does not have an easy antiderivative at all. So don't try to take the antiderivative of it. People always try to do that, and it's always going to lead them astray. Just remember that when we take the derivative of a negative function, we'll get a negative. The negative is a constant that we can factor out. And we're just going to replace the derivative and the integral cancel each other out. We're going to replace the t with the x, and we're going to get sine of x squared. And that is it. Don't do more than you have to. All right. So again, I don't want to try to integrate this. It is possible. We'll learn some techniques later on that will show us how to integrate something like this. It would be a mess, but we could do it. But we don't have to. Because all we're doing is taking the derivative of the integral. They're going to cancel each other out. We're going to take our variable, and we're going to replace t with that variable. But there's a trick here. We're going to replace the t with an x squared, just like we would if it were an x. Everything else just gets copied down. We're just going to replace every single t with an x squared. So this t squared becomes x squared squared, or x to the fourth. That's not the trick. That's a pretty basic little thing. Does anyone see the extra piece here? Well, this is not an h of x problem. This is an h of x squared problem equals that, right? So this is not an input of x. This is an input of x, x squared. So if I take the derivative with respect to x of h of x squared, well, I mean, the argument never changes. We know that, right? We'll take the derivative of h, evaluate it at x squared. But don't forget the chain rule. The argument here is not x, it's x squared, so we have to make sure we multiply by the derivative of that argument. So that's going to be an extra piece that people tend to forget. Please do not be one of those people who forgets it. You can distribute that 2x into the numerator. You can just leave it factored in the numerator. You can leave it like that. I don't really care. Just don't forget it. Don't forget the chain rule. All right, and then we can combine it all together into both of the little curveballs into one. I don't know if two curveballs cancel each other out. I don't think so. It just makes it curvier, right? So the variable expression is at the bottom. We have to flip it around to the top, so that's going to be a negative. And then we're going to replace the t with the variable expression. So the 23 is going to be replaced, is not going to be replaced. The t is going to be replaced with the cosine of x. But don't forget the chain rule. The chain rule is multiply by the derivative of the argument. The argument is cosine of x. The derivative of that is negative sine of x. Now we could leave the answer like that, but of course we're not, because we know trig, and trig is our friend. We're going to make sure that we can reduce this. First of all, negative times negative is positive. We've got a coefficient of 23, and sine of x divided by cosine of x, we all know that to be tangent of x. So that's a nice final answer. You better believe that on a multiple choice question, you're not going to see this as the answer choice. You're going to see something more like this.